What if I told you that India has built a railway through some of the most dangerous mountains on Earth? A railway where engineers had to blast through solid Himalayan rock, construct hundreds of kilometers of tunnels, and build bridges higher than the Eiffel Tower. For decades, many experts believed this project was nearly impossible. The Himalayas are known for earthquakes, landslides, extreme weather, and some of the toughest terrain on the planet. Yet India's engineers refused to give up. Today, this incredible railway is transforming connectivity, bringing remote regions closer to the rest of the country, and showcasing one of the greatest engineering achievements of the 21st century. In this video on Datascope, we'll explore how India drilled through the mighty Himalayas to build one of the world's highest and most challenging railway networks, the groundbreaking technologies used, the obstacles faced, and why this megaproject is changing the future of transportation forever. Let's begin. I recognize the bridge as one of the most extreme and impressive railway bridges in the world, holding the global record at 359 meters above the riverbed. It stretches approximately 1,315 meters in length, with a main arch span of 467 meters. Constructed using over 30,000 tons of steel and designed for at least 120 years of operation. Construction began around 2004, with significant work starting in 2010 and took nearly 2 decades to complete at an estimated cost of $1.3 to $1.5 billion. What sets this bridge apart is its location deep within the Himalayas, where sheer cliffs drop almost vertically and the Chenab River flows 359 meters below the deck. Engineers faced immense challenges due to the extreme terrain and lack of infrastructure, as the harsh conditions offered no natural ground or conventional workspace to build upon.
How to even reach the construction
Reaching
site.
the construction
There were
site
no
required
roads,
building
no
a
access
road
roads,
from scratch
and no
due to the
viable way to
absence of
transport
access
heavy
roads
machinery.
and
The only
transport options
solution
for
was
heavy
to build a
machinery.
road from
I
scratch.
designed a 26-kilometer route through solid rock
A roughly
along steep
26-kilometer
mountain
route
slopes,
was
which
designed to
became an
cut through
intense
solid
engineering
rock,
project
winding
where
along
each
steep
meter
and
gained
dangerous
involved
mountain slopes.
significant time,
But this was far more than
effort,
ordinary
and
road
risk.
construction.
Workers
It became a
suspended themselves on
standalone
near
engineering
vertical
project
cliffs,
where every
using
meter gained
handheld
came at the
drills
cost of
to
time,
penetrate hard
effort,
granite
and risk.
as they carefully
The
placed
work began on
explosives
near
to
vertical
fracture
cliffs.
the rock
Workers had to
without
suspend
causing
themselves
collapses.
with safety
The
harnesses,
process involved
operating in
thousands of
midair
small
as they drilled
blasts
into the
over
rock.
several years,
Each hole was
with
made using
specialized
handheld
excavators
drills,
clearing
penetrating
debris
granite
to
with
gradually
compressive
create
strength
a
reaching
narrow
100
roadway.
to 250
Stabilizing the
mph,
exposed
far
rock
harder
faces
than
with
conventional
steel
concrete.
mesh and shotcrete
Explosives were then
proved
carefully
just as
placed using
crucial
pre-split
to prevent
blasting
landslides
techniques,
and
allowing
support the
engineers
new
to fracture the
infrastructure.
rock along precise.
In an environment where even minor shifts in terrain could trigger serious accidents, controlling every centimeter of rock was critical under relentless winds and unstable ground. Progress was painfully slow, averaging only a few meters per day, which took years to complete the access route. Once access was established, the next challenge involved transporting over 30,000 tons of steel to heights deep within the Himalayas. The newly carved roads were narrow and filled with tight hairpin turns, making it nearly impossible to use oversized heavy transport vehicles. Consequently, the entire steel supply had to be broken down into thousands of smaller plates and modules, each weighing between 5 and 20 tons, suitable for standard trucks. Every trip involved navigating perilous mountain roads at very low speeds, transforming what seemed like short journeys into several-hour-long treks. Thousands of trips over many years were necessary to transport the required materials, each fraught with risks like slipping wheels and overturned vehicles. Once the steel plates were delivered, the true challenge began as there was still no bridge to show for the effort. Engineers set up a temporary fabrication yard on the cliff's edge to weld thousands of steel plates into large structural components, each weighing between 10 and 50 tons. The process required incredible precision, as even minor deviations could lead to significant errors, jeopardizing the entire structure's integrity. Every weld I worked on had to be precise and strong enough to withstand thousands of tons during operation while enduring extreme temperature fluctuations and constant vibrations for over 100 years. To ensure quality, I ensured that every weld was inspected using ultrasonic testing or industrial X-ray imaging to detect even the smallest internal defects. In an environment with constantly changing conditions, maintaining this level of precision was crucial for the entire structure's integrity. After fabricating and welding the steel components on site, I moved on to the foundation construction, which involved drilling directly into the rock of the Himalayas instead of building on soil. I oversaw the excavation of deep foundation pits and the pouring of thousands of tons of reinforced concrete to create massive support bases capable of bearing immense loads on each end of the bridge. The bridge structure was anchored into foundations with high-strength bolts and steel anchors, integrating the mountainsides into the load-bearing system. This design allowed forces from the bridge and trains to be transferred into solid bedrock, avoiding reliance on weaker soil layers. Upon completing the foundation bases, the bridge still lacked a critical component for accessing the central span suspended across a nearly 500-meter void. Without any ground or intermediate support, conventional cranes were inadequate for the construction zone. To overcome this, I utilized a massive aerial cable crane system with tall steel towers erected on opposing mountaintops as anchor points. Started by observing the engineers connect two ends of a project from almost nothing, using a helicopter to pull a thin pilot line across a deep valley. From this initial line, hydraulic winch systems gradually pulled larger cables into place until the main cables, capable of carrying hundreds of tons, were fully installed. This transformation turned the space above the valley into a functioning transport system, allowing suspended cabins to move steel components weighing between 10 and 25 tons with high precision. As the aerial cable crane system became operational, the critical phase of assembling the steel arch in midair began, with steel segments lifted and moved into position without any scaffolding below. I watched as each section was meticulously placed and welded together in midair, with a 359-meter drop beneath, highlighting the precision required for this daring operation. Achieving near-perfect accuracy was essential, with tolerances measured in millimeters due to the challenges posed by changing conditions such as wind and temperature. High-pressure concrete was pumped into hollow steel tubes, creating a composite structure that combined steel for tension and concrete for compression, enhancing the arch's stiffness and vibration resistance. The critical moment arrived when the two halves of the arch were aligned and the final locking segment was installed, allowing it to become a unified structure. The transition from a temporarily supported system to a self-supporting arch marked the bridge's true inception, with a steel arch firmly standing in midair. To construct the deck, engineers opted for the incremental launching method, fabricating steel and concrete segments at ground level and extending them into midair using hydraulic jacks. Witnessed a hydraulic system generate thrust forces that allowed a 1.3-kilometer deck structure to slide forward precisely without scaffolding. Gradually, the deck connected two cliffs, transforming an impossible gap into a functioning railway route, completed around 2023 to 2024. The Chenab Bridge enabled year-round rail connectivity for the Kashmir region, replacing unreliable road transport. Travel times have decreased significantly from dozens of hours to just a few hours, while transportation costs have lowered as trains can carry large quantities of goods efficiently. The railway's strategic importance is evident, as it enhances connectivity in a geopolitically sensitive area, facilitating both civilian and emergency movements. Alongside the massive scale and impact of the project, I face considerable challenges, with total construction costs estimated between 1.3 and 1.5 billion US dollars and a nearly 20-year timeline due to its complexity. Maintenance over its lifespan of 100 to 120 years will be a long-term burden, especially in harsh natural conditions. The bridge must endure extreme winds, temperature fluctuations, and risks of earthquakes, necessitating constant inspection and maintenance at high cost for safe operation. As part of a crucial railway line spanning 272 kilometers, Any disruption poses a risk to the entire transportation system, creating significant dependency on this infrastructure. Additionally, the bridge's location in Jammu and Kashmir, a geopolitically sensitive area, exposes it to potential security risks. Conclusion. The story of India's Himalayan Railway is a story of determination, innovation, and engineering excellence. Against enormous odds, engineers drilled through mountains, crossed deep valleys, and overcame some of the toughest geological conditions on Earth. What many considered impossible has become a reality. Today, this remarkable railway stands as one of the world's greatest infrastructure achievements and a powerful example of what human ingenuity can accomplish. If you enjoyed this video, don't forget to like, share, and subscribe for more incredible stories about engineering marvels, megaprojects, and the technologies shaping our future. Thanks for watching, and we'll see you in the next video.